The universe is a place of rules, immutable, elegant, unflinching laws that bind everything from the orbit of planets to the spin of atoms. Gravity pulls, thermodynamics balances. Light travels at a fixed pace through the vacuum. Across these constants, the cosmos unfolds like an ancient symphony. Complex, yes, but always predictable, always loyal to its own mathematics. When a comet arcs toward the sun, it performs choreography older than language, a dance we've traced and forecast for centuries. Its path, brightness, and decay, all written in equations we can trust. But every once in a while, the cosmos does something that makes even the most confident astronomers hold their breath. This is a story about one of those moments. It began quietly, as all discoveries do, with a dot of light moving through Virgo's stars on the first night of July 2025. The survey system that found it, Atlas, has seen thousands of such wanderers. It catalogs comets, asteroids, fragments of ice and rock that drift near the inner solar system, visitors from its own frozen edges. But this one was different. When the data came in, when orbital parameters were computed, every researcher involved saw the same astonishing number: eccentricity greater than 1. That single mathematical value means freedom, escape velocity achieved, orbit unbound. The object wasn't from here, it was from somewhere beyond, an interstellar traveler. They called it 3I Atlas, the third known interstellar object in human history. And at first, everything about it was perfect, normal, even comforting. It behaved as any comet should. It brightened as it approached the sun. It flared into a magnificent tail, shimmering with ionized gas and dust. It curved inward to its closest point, its perihelion, at roughly 2/3 of an astronomical unit, just inside the orbit of Venus. Astronomers watched, delighted. Instruments recorded spectra, light curves, coma structure. The data was clean. The models held true. When you've spent your life deciphering the language of celestial motion, moments like that are joy. The universe speaking exactly as expected. But the story didn't end there. It couldn't have. By September, 3I Atlas should have been fading. Its outgassing should have waned as it retreated from the warmth of the sun. That's how comets behave. The energy fades, the ice locks back into silence, and the visitor drifts outward into the dark, cooling and dimming. Yet in mid-October, something strange happened. A hobbyist in Australia, peering through his modest telescope, noticed the comet was brighter, not dimmer, than before. He thought it must be an error, but within hours, other observers confirmed it. 3I Atlas was defying physics. Professional telescopes turned their attention back toward it, and what they saw over the following nights sent ripples of confusion across observatories worldwide. The object wasn't merely glowing brighter, it was accelerating. Instead of slowing under the sun's diminishing pull, it was speeding up, like a car pressing gently on the gas. And the direction of that acceleration didn't make sense either. Outgassing, the sublimation of ice into gas, always pushes a comet slightly away from the sun. But 3I Atlas was being pushed forward along its trajectory, as though something were propelling it deliberately. Imagine being an astronomer staring at a monitor that tells you the universe just broke one of its oldest promises. You check your equations, your calibration, your sanity. You run the numbers again. But the data doesn't lie. Every telescope that looked saw the same thing. An interstellar comet accelerating in ways no natural body should. To understand why this is so unsettling, we have to recall what normal looks like. Comets are frozen relics, archives of primordial material that have slept for billions of years until the sun's light wakes them. As they warm, their ice turns to vapor, venting jets that act like tiny thrusters, altering their orbit slightly. These accelerations are weak, subtle, and predictable. They happen close to the sun when the heat is strongest. and fade quickly as the object cools. But 3I Atlas's acceleration began after it passed perihelion, when the heat should have been too faint to matter. This is the moment that transformed a routine observation into a cosmic enigma. A mystery unfolding in real time, with every data stream pointing toward a conclusion no one wanted to reach. That something about this object, something fundamental, refuses to obey the rules. By early November, astronomers had gathered enough data to confirm the impossible. At a distance of roughly 1.5 astronomical units from the Sun, the comet was accelerating at a rate of nearly 5 millimeters per second squared, 5 times stronger than the famous acceleration seen in Oumuamua 8 years earlier. For a frozen fragment hundreds of meters across, that's enormous. To maintain such motion would require energy far beyond what sublimating ice could supply. The energy didn't add up. The vectors didn't align, and the light curve, the record of how the comet brightened and dimmed, showed that it was spinning faster over time, its rotation period shortening, as though an invisible torque was acting upon it. The astronomers began to whisper, then to write carefully worded memos. The Minor Planet Center issued a neutral bulletin requesting additional observations. NASA and the European Space Agency made public statements emphasizing complex activity requiring further study. The words were cautious, but beneath them ran an undercurrent of unease, because what they were all watching, a comet accelerating away from the Sun, shouldn't exist. In scientific history, there are moments when our understanding of the cosmos fractures, when one observation becomes the seed of a paradigm shift. The motion of Mercury that defied Newton until Einstein rewrote gravity. The ultraviolet catastrophe that birthed quantum mechanics. Each began as an anomaly. Now, in the autumn of 2025, another anomaly glowed faintly in the night sky, leaving astronomers with a question so large they could barely speak it aloud. What if this isn't just another comet? What if we're witnessing a phenomenon that belongs to a category we've never defined? That's where we stand at the close of this first act, under a sky filled with silence, watching a small object accelerate into the dark, rewriting equations as it goes. Something is happening out there, something that challenges the most fundamental principles of motion, energy, and the quiet certainty with which we thought we understood the universe. And the strangest part? It's still happening now. When the first verified reports began to circulate through the astronomical community in late October, what had started as a curiosity swiftly evolved into an international scientific emergency. The numbers didn't fit, the energy didn't balance, and the behavior of the comet known as 3I Atlas challenged the very laws that underpinned celestial mechanics. In laboratories, observatories, and university offices across the world, researchers began recalculating, reanalyzing, and rethinking everything they believed they knew about how a comet should behave once it had rounded the Sun and begun its long retreat into space. The timeline of the discovery is now being reconstructed with almost forensic precision. After its closest solar approach on August 15, 2025, 3I Atlas behaved impeccably for nearly 2 months. The coma expanded and then contracted. The spectral lines of water vapor and carbon dioxide faded exactly as expected. Astronomers shifted their attention to other targets, logging the comet as one more interstellar visitor whose trajectory was mathematically well understood. But in the second week of October, a simple observation by an amateur observer from New South Wales became the spark that reignited the world's scientific attention. His recorded brightness did not match predictions. The deviation was small but undeniable, and when 3 other observers confirmed the anomaly, the data began to cascade through professional networks. Within days, observatories in Chile, Hawaii, and the Canary Islands swung their telescopes back toward the outbound visitor. The first photometric results, analyzed by a team at the European Southern Observatory, revealed an increase in luminosity by almost 1 full magnitude since the previous month. This brightening alone was extraordinary, but it was the accompanying astrometric data, the precise measurement of the comet's position relative to background stars, that truly stunned the researchers. The object was not where gravitational models said it should be. It was slightly ahead, and the discrepancy was increasing with each passing day. For a comet roughly 600 meters across and estimated to weigh between 10 and 50 million kilograms, the measured acceleration, approximately 4 to 5 millimeters per second squared, was monumental. Small, perhaps, to the casual listener, but vast in astronomical terms. To sustain such motion, the object would require continuous thrust on the order of tens or even hundreds of kilonewtons. Natural outgassing could not plausibly generate such power at a distance where solar heating had already diminished by more than half. Every physicist familiar with cometary dynamics recognized what the numbers implied. Something was providing energy that the comet should not possess. The initial response was the same everywhere: check for error. Instrumental biases, calibration faults, software glitches, these are the ghosts that haunt observational science. But as independent teams from separate continents compared results, the conclusion became unavoidable. The measurements were real. Different telescopes, different methods, all pointing to the same conclusion. 3I Atlas was accelerating in the wrong direction and by the wrong magnitude. By October 28th, astronomers at the Harvard-Smithsonian Center for Astrophysics issued a preliminary report to the Minor Planet Center, whose understated wording concealed deep unease. Object exhibiting non-gravitational motion inconsistent with standard sublimation models. In the restrained dialect of scientific communication, that phrase was the equivalent of a siren. What followed was the largest coordinated observation campaign ever undertaken for an interstellar object. The Keck telescopes in Hawaii began high-resolution spectroscopy, measuring emission lines across optical and near-infrared wavelengths. The results came back confusing. Water vapor emission was weak, carbon monoxide and dioxide almost absent, while sodium and iron lines, usually faint and transient in cometary spectra, were unusually strong and persistent. Even more perplexing, the ratio of ionized to neutral species suggested processes requiring temperatures far higher than any plausible sublimation. Meanwhile, the Hubble Space Telescope dedicated several orbits to imaging the coma. The images showed a smooth, symmetrical envelope of dust and gas without jets or asymmetries that could explain directional thrust. The nucleus appeared stable and singular, with no fragments or debris clouds visible down to a resolution of a few hundred meters. Ground-based adaptive optics confirmed these findings. The comet was intact. No breakup, no violent ejection events, no mechanisms visible that could produce the required torque or acceleration. In an effort to reconcile observation with theory, researchers constructed increasingly elaborate models. Some proposed that the comet's composition included hypervolatile ices, nitrogen, methane, or carbon monoxide, that could sublimate at extremely low temperatures, providing additional thrust even at large solar distances. Others speculated that 3I Atlas might contain exotic amorphous ices capable of storing latent heat and releasing it episodically, much like a slowly detonating thermal battery. But the math refused to cooperate. Even under the most generous assumptions of composition and temperature, the energy output fell short by an order of magnitude or more. At the same time, rotational analysis introduced a new mystery. Using light curve variations, minute fluctuations in brightness caused by the comet's spin, astronomers determined that its rotation period was shortening. In August, before perihelion, 3I Atlas rotated once every 8 hours and 12 minutes. By late October, that period had dropped to about 7 hours. The nucleus was spinning faster, gaining angular momentum when it should have been losing it as outgassing subsided. A comet cannot simply spin itself up without an external or internal torque. and yet this one did. The implication was unsettling. Whatever force was propelling it linearly was also acting rotationally, as though the two motions were coupled by design. The community divided into camps, each championing a different hypothesis. The chemical faction argued for unknown ices, possibly formed in an alien protoplanetary environment with chemistry foreign to our solar system. The structural group suggested a hollow or porous interior that could magnify the effects of internal gas flow, creating localized jets aligned by chance with the comet's motion. A smaller, more speculative group proposed electromagnetic coupling, in which interactions between the solar wind and the comet's induced magnetic field could transfer momentum through plasma processes we barely understand. None of these models fit all the data simultaneously. Each explained one aspect while contradicting another. As the days progressed, the discrepancies grew too large to ignore. By November 1st, the positional error had increased to more than 400 kilometers compared to purely gravitational predictions. The comet was, quite literally, outrunning its own equations. On November 3rd, the Minor Planet Center released a terse bulletin requesting additional observations to improve orbital determination of Object 3I 2025 Atlas. Between the lines, everyone understood what that meant. Verify the impossible. The James Webb Space Telescope entered the scene a few days later, its infrared instruments capable of detecting the faintest thermal emissions. If the comet were expelling gas or dust at rates sufficient to accelerate it, the heat signature should have been obvious. But Webb's results only deepened the puzzle. The measured thermal emission was far lower than expected for an active comet of that brightness. In other words, the object was shining without radiating the heat it should. Energy was being expended in one form but not another, a violation of thermodynamic intuition. In Zurich, astrophysicists ran simulations of the comet's motion under a variety of hypothetical thrust profiles. The only models that reproduced the observations required a continuous, directional acceleration perfectly aligned with the velocity vector, exactly the orientation an engineer would choose to optimize propulsion efficiency. Such precision alignment was statistically absurd for natural outgassing, which typically produces thrust vectors that wobble as the nucleus rotates. Yet the acceleration of 3I Atlas remained astonishingly steady, within 15 degrees of constant alignment over weeks of observation. At NASA's Jet Propulsion Laboratory, teams recalculated the object's trajectory using updated data. The results predicted that by mid-December, the comet would be traveling faster than any natural object ever recorded leaving the solar system. The question, whispered in private meetings and late-night conference calls, was simple and terrifying. How? Scientists are cautious by nature. They know the universe occasionally plays tricks of perspective, that apparent anomalies often dissolve under deeper scrutiny. So they kept testing. On November 4th, an international astrometry campaign began, involving observatories from 5 continents. Using differential measurements of the comet's position against reference stars, they achieved angular precision measured in hundredths of an arcsecond, equivalent to detecting a coin's motion from hundreds of kilometers away. The results were consistent across every site. The comet's path curved ever so slightly, but unmistakably, away from the gravitational prediction, accelerating smoothly along the direction of travel. At this point, discussions turned to the energy budget, the fundamental accounting of power and motion. If the comet weighed roughly 50 million kilograms, maintaining its measured acceleration for just one day required energy output equivalent to detonation of several kilotons of TNT. Over a month, that equaled the energy release of a small nuclear weapon. No conceivable natural mechanism could sustain such power so precisely directed for so long at that distance from the sun. The numbers were merciless, and they told a single story. The comet was doing work. In parallel, spectroscopic analysis revealed something even more puzzling. The coma's chemical fingerprint included weak but distinct lines from complex organic molecules. aromatic hydrocarbons, long-chain carbon compounds, even traces of what appeared to be metallic organics, molecules that bind metal atoms to carbon frameworks. These are rare in comets. Their presence suggested chemistry that either originated in an environment very different from our solar nebula or was the result of processes entirely unknown. Some lines didn't match any known spectra at all, leaving analysts staring at unidentified peaks with no reference to compare them to. By November 6th, the object's increasing brightness began to draw attention beyond scientific circles. Headlines appeared in a few specialized outlets, cautiously noting unusual activity in an interstellar comet. Public statements remained subdued, emphasizing the excitement of studying a complex natural phenomenon. But behind the scenes, urgency was rising. There were quiet discussions within space agencies about the feasibility of launching a rapid response mission, a small probe using high-efficiency propulsion that could intercept 3I Atlas before it escaped completely. The calculations were disheartening. Even with the most optimistic launch scenarios, the probe could not catch it. The window had closed weeks earlier, before the anomaly was recognized. Humanity could only watch from a distance as the mystery accelerated away. The SETI Institute, never shy of bold inquiry, devoted several sessions of the Allen Telescope Array to listening at multiple frequencies, focusing particularly on the hydrogen line near 1.42 gigahertz, a universal marker that any radio-capable civilization would recognize. For 6 nights they listened. The official report stated there were no narrowband signals indicative of artificial transmission, but internally, the data showed a faint, persistent noise spike hovering just above background levels, constant in frequency and spatially coincident with the comet. It was too weak for confirmation, too structured to dismiss outright. The scientists involved have chosen their words carefully. Statistically interesting, but inconclusive. Meanwhile, the rotation data continued to evolve. The spin-up rate accelerated slightly, and faint periodic fluctuations suggested a possible secondary modulation, a tremor or oscillation repeating every 28 minutes. Some suspected precession, others hypothesized internal mass movement, as though something inside the nucleus were shifting. If true, it implied a dynamic interior rather than the inert frozen mass expected of comets. In a world already accustomed to extraordinary astronomical events, 3I Atlas became something more than a curiosity. It became a test of our frameworks. Every explanation added complexity without resolving the core paradox. How could an object with no detectable energy source maintain acceleration in defiance of gravity, conservation of momentum, and thermodynamic limits? By mid-November, the data volume had grown immense, terabytes of spectra, imagery, and positional readings, yet the pattern was unchanged. The acceleration persisted, the direction remained constant, and the brightness fluctuated unpredictably as if governed by an unseen mechanism. Papers were drafted, reviewed, withdrawn, and redrafted as new data undercut old theories. The tone of professional correspondence shifted from skepticism to fascination to a kind of hushed anxiety. Some researchers began exploring unorthodox avenues, proposing mechanisms that, only months earlier, would have been dismissed as science fiction. Could the comet be interacting with dark matter in some unique way, converting it into kinetic energy? Could internal superconducting materials be generating electromagnetic thrust through interaction with the solar wind? None of these ideas survived detailed analysis, but their emergence signaled the growing realization that the usual boundaries of explanation might not suffice. As the comet receded toward the outer solar system, its velocity climbed. Projections indicated that by January it would cross the orbit of Mars at speeds exceeding 40 kilometers per second, placing it beyond practical observation range soon after. Astronomers rushed to extract every bit of information they could before the data stream faded into static. Each night's observations brought more questions. Small flashes of unexplained light appeared in spectrographic records, brief, intense emissions lasting seconds, then vanishing. They were interpreted variously as micrometeoroid impacts, electrical discharges, or energy releases of unknown origin. Across disciplines, the conversation shifted from the narrow technicalities of cometary physics to the broader implications for science itself. If 3I Atlas could not be explained through known mechanisms, what did that say about our understanding of natural law? Was this the herald of an undiscovered class of astrophysical phenomena, or something more deliberate, something engineered? Most scientists avoided that word, but it lingered in the margins of every discussion. The parallels were too precise: directional thrust, consistent acceleration, internal torque, absence of fragmentation, all behaviors one might expect from a controlled object rather than a chaotic one. In early November, an internal memo circulated within NASA's Planetary Science Division concluded with a single, understated line: "Further observation recommended, potential paradigm-defining object." It was bureaucratic phrasing for an existential question. If this comet was acting under control, whose control? Yet amidst all the speculation, the data remained stubbornly real. The acceleration was measured, the spectra recorded, the trajectories confirmed. There was no doubt about the phenomena themselves. The doubt lay only in interpretation. And as the days grew colder on Earth, a frozen traveler far beyond Venus's orbit continued to defy gravity, spinning faster, glowing brighter, and quietly rewriting humanity's understanding of what is and what is not possible in the orderly mechanics of the cosmos. To understand the significance of 3I Atlas, we have to step back, far back, beyond the immediate data and the debates that consumed observatories in late 2025, and look at the larger arc of how humanity has watched and understood its visitors from the stars. Because this object, whether ultimately explained by natural chemistry or something more extraordinary, belongs to a lineage that stretches across centuries of curiosity, fear, and wonder. Every comet ever observed has told us something about the universe, but very few have forced us to question the universe's most fundamental assumptions. When astronomers think of comets, they think of time capsules, fragments from the dawn of planetary formation, unchanged for billions of years. They are the raw material from which planets were built. But 3I Atlas was not born under the same sun as Earth or Mars or even Jupiter. Its atoms, its frozen gases, its dust grains were assembled around another star in another system, under conditions we can only imagine. Its chemical fingerprint, so unfamiliar, is a record of alien creation. That alone would make it one of the most important discoveries in human history. Yet it offered more than composition. It offered behavior, motion that ignored our equations, light that refused to fade, energy that appeared without cause. In Cambridge, astrophysicists now compare 3I Atlas to a mirror held up to our ignorance. It is, as one researcher put it, a physics exam we didn't study for. Every new spectrum, every rotational data point, every anomalous flash of emission is another question scrawled across the sky, asking whether we truly understand the mechanisms that govern celestial bodies. The comet is already beyond the reach of most telescopes now, but the data it left behind will occupy the minds of scientists for decades. Among those who have devoted themselves most passionately to unraveling its mystery is Dr. Maren Calloway, an orbital dynamicist at the University of Arizona. In early analyses, she noticed the first subtle hints of the acceleration anomaly. Her email to colleagues was cautious: 3 lines of data and a single sentence beneath them. If correct, this isn't sublimation. Since then, she has led one of the key international teams attempting to model the object's motion. In interviews, she has spoken softly, almost reverently, about what the experience has meant. "We're witnessing something that humbles you," she said. "It's as though the cosmos is whispering that there are still doors we haven't opened." Another figure who has emerged quietly from this saga is Dr. Tenzin Arora, a spectroscopist with the Indian Institute of Astrophysics. Arora's group was among the first to identify the unidentified emission lines in the comet's light, features that did not correspond to any known terrestrial element or molecule. For weeks, they combed through spectral libraries, running cross-references with databases of laboratory emissions, mining every known chemical compound, but nothing matched. In a recent conference presentation, Arora described the frustration and fascination of those nights. We kept asking, are we looking at chemistry we don't recognize or physics we don't yet understand? The comet story also belongs to the engineers and observers who never looked through the eyepiece directly, but who built the instruments capable of seeing what the naked eye could not. The technicians who cooled the detectors on the James Webb Space Telescope to within a few degrees of absolute zero. The programmers who wrote algorithms to stabilize the Keck adaptive optics mirrors in the unpredictable turbulence of the Hawaiian night air. The amateur astronomers whose backyard observations filled gaps in professional data. It is a collective achievement, a global act of curiosity that spans from hand-assembled telescopes to billion-dollar orbiting observatories. Historically, humanity has been here before. The late 19th century had its unexplained lights in the heavens, its irregularities in Mercury's orbit, its anomalies that hinted at deeper truths. Those puzzles gave birth to revolutions, relativity, quantum mechanics, new cosmologies. Perhaps Three-Eye Atlas will do the same. Perhaps the strange acceleration will force us to refine our understanding of how momentum and radiation interact in vacuum, or reveal new states of matter stable only in interstellar cold. Or perhaps it will remain, like the great mysteries of the past, a question without an answer, a cosmic riddle whose solution lies forever beyond our reach. Whatever the outcome, it has already changed how astronomers think about interstellar visitors. The first, Oumuamua, was the herald, featureless, silent, but oddly propelled. The second, Borisov, reassured us with its normalcy. And now the third, Atlas, has brought the mystery roaring back, amplified and undeniable. The pattern emerging is not just statistical but philosophical. We are beginning to understand that interstellar space is not empty of stories. It is filled with travelers, some ordinary, some extraordinary, each bearing the imprint of the stars that birthed them. If Three-Eye Atlas is natural, it means nature is capable of engineering mechanisms we have not yet imagined. If it is not natural, if it was built or modified by intention, then we are no longer the only engineers the cosmos has produced. Either answer expands our world in ways no equation can capture. The boundaries of known physics would blur into something new, a larger framework where our current laws are simply approximations, valid only within the small comfort zone of our local system. There are already whispers of missions being conceptualized for the next generation of interstellar objects. Fast launch probes using solar sails, plasma drives, or compact fusion engines that could be readied within weeks of a new discovery. The Vera Rubin Observatory in Chile, scheduled to survey the sky continuously, is expected to find dozens of new interstellar objects each decade. The lessons from Atlas have been heard. Never assume the ordinary. Every faint streak of light could be another messenger, another fragment of the galaxy's long conversation with itself. Scientists are also looking inward, questioning the assumptions baked into the equations themselves. The mathematics of sublimation, of non-gravitational acceleration, of radiative transfer, all are being revisited in the light of this anomaly. New laboratory experiments are being proposed to replicate the conditions of deep interstellar cold, to test whether unknown phase transitions or quantum scale effects might release energy in unanticipated ways. It is meticulous, patient work, the kind of science that requires humility as much as brilliance. And yet, outside the strict boundaries of the laboratory, Three-Eye Atlas has become something more than a scientific puzzle. it has become a symbol, a reminder of how little we truly know. For the public, the story carries echoes of wonder and unease, of cosmic loneliness, and the possibility of companionship across light years. For those who dedicate their lives to studying the heavens, it represents the frontier of knowledge itself, the point where observation and imagination meet. In the months since its discovery, the comet has already receded beyond the orbit of Mars, its faint glow slipping into the noise of the background stars. Soon, it will be invisible even to the most powerful telescopes. It will continue on its hyperbolic path, outbound toward the constellation Lynx, destined to drift for millions of years through interstellar night. But the data it left behind, its trail of photons, spectra, and trajectories, remains. Astronomers will study it long after the object itself has vanished from the sky. Perhaps one day, another civilization, orbiting another star, will look up and see this same object, a dim speck crossing their skies, and wonder about its origin, just as we wonder now. They will point their instruments at it, record its light, trace its impossible acceleration, and ask the same question that now haunts us. How can a thing move without a source? Maybe they too will come away humbled, reminded that the universe is not obligated to make sense within the confines of any single species' understanding. In the end, the story of Three-Eye Atlas is not only about a comet,